Hi, I'm Dr. Elisa Dimena, and today I'm going to talk to you about the smallest units of muscle and how a contraction is facilitated by some key proteins. So we're going to start at looking at the level of the muscle fiber or the cell. We're also going to look at some important larger structures such as the sarcolemma and the sarcomere, and of course the tiniest components, things like important ions such as calcium, as well as the role of actin and myosin as it facilitates the contraction process of muscle. Now, let's take a look at this image from your book. So this is the anatomy of a skeletal muscle fiber, also known as a skeletal muscle cell. So there's a couple of important parts. First, let's review a few things, such as here's some nuclei, right? They're pushed up against the side because they're so packed, so densely packed with these myofibrils. All these myofibrils are important because they contain these little stripy segments known as the sarcomere. Now, the sarcomere is important. A sarcomere is the fundamental contractile unit of muscle. It's the whole place where all of the contraction process starts, and since all of them are stuck together in this nice set of rows and then layered and layered upon each other in these giant bundles, it allows entire large muscles to expand and contract, or I'm sorry, relax and contract in the contraction process. And let's see here, what else? Oh, great, of course, mitochondria. Can't forget those guys. So, as you can imagine, muscle contraction and even relaxation to some point is going to use a ton of ATP, right? The energy currency molecule of the cell. So mitochondria are there in mass, embedded between these myofibrils to make sure that that ATP is present and that these structures are supported so that contraction can be carried out properly. The other thing to know about is this structure. This is the sarcolemma. It's like the cell membrane. We're going to look at some structures that lie just underneath that sarcolemma. Let's see what else. Oh, of course, the light band and the dark band. As you'll notice, the stripy pattern kind of follows like a light and dark alternation, right? So there's a light one, then a dark one, then a light one, then a dark one. And that's important too, because those signify the positions of those two key proteins that I mentioned on the first slide, actin and myosin. We're going to look together at how they alternate and how they interact with each other to carry out the process of contraction in muscle. All right, so here's the microscopic anatomy of a muscle fiber as seen through a microscope. Okay, as you can see, this has been enlarged 700 times. That's huge. So it's actually a teeny tiny section of a huge muscle cell. So again, just like last time, we've got all of these nuclei, multinucleated cells, and they're kind of pushed up towards the sarcolemma of all of these muscle fibers, or well, these 3 to 4, it looks like, muscle fibers. Also, you'll see a photographic image of those important alternations, those striations, those little lines we see. They're alternations of a dark, what we call A band, and the lighter color one we call the I band. All right, so what's inside of all those stripes? Let's take a look. So this is what I referred to earlier on as the sarcomere, or the fundamental contractile unit of muscle. This is the little thing that does all the work, that makes those big muscles contract and relax. So it all happens here with a similar type of motion. First, let me show you around. All right, so in this section, here, let's get the color specific. Right, here we go. In this section here, as you'll see, it repeats on and on. There's these little stripes, right? Little red stripes is shown here. And what's important about them is they're kind of thicker than the opposite ones, which are right here, which also, as you can see, form a pattern. Those are thinner ones. So as you can see, it goes yellow, blue, yellow, blue, yellow. So just like the striations of the muscle fiber itself, except this is on a smaller level. So let's talk about those. So the first one I mentioned was this red one, right? Actually, here's a red one. I don't know, that makes a little more sense, right? Okay, so those are the thick filaments, myosin. Again, known as the thick filaments, okay? Quite frankly, because they're just thick in size. They're just thick, okay? We'll see what that looks like in a little bit. The next one is going to be this one. These are the actin filaments, right? Actin, which are known as the thin filaments, because compared to myosin, they're kind of thin. And there's a couple of things you need to know about actin and myosin. Number one, They overlap a little bit with each other, as you can see here. Oh gosh, I sure have a lot of stuff. Let's erase a few things. There we go, that's a little better. Okay. So as you can see here, there's these zones of overlap right here. And then there are these zones where there is no overlap, right? Where it's either just pure myosin or pure actin, okay? So the zones of overlap are important because that's where actin and myosin can actually come together and grip. And so as a contraction works, myosin will grab actin and pull it closer and closer. So this sarcomere, for example, looks like it's probably contracted a bit. Okay, as you can see, there are overlaps between the actin and the myosin. All right, let's go ahead and move on. So here's a little bit of a step-by-step drawing of a sarcomere, just looking at the actin and myosin filaments. Okay, so this would be relaxed muscle, right? Shown here. It's muscle at its greatest, longest length, right? So it's pretty long. Here's end to end on this one. As you can see, there's the least amount of overlap in the actin and myosin too. So these are also relaxed. These are relaxed sarcomeres. So when a contraction begins, the myosin begins to grab and step and pull the actin closer and closer to its center line, or the M disc. As it starts to contract, it eventually goes to, and this is like a fully contracted state, right? Fully contracted. And as you can see, the sarcomere now is physically smaller. So here's the lines of where we started out, right? There's a gap now because it became physically smaller, right? Everything's pulled in tighter together. The same thing happens here when we look at the actual muscle at the organ level. So here is where you would see it's taking up a little, except for that one. I got a little crazy. Okay, there we go. You can see that compared to its relaxed state, which is right here, we've actually lost quite a bit in the length. So all of those sarcomeres together contracting shorten the muscle overall. And then we have more overlap, right? So the overlap here is thicker, resulting in thicker contraction, or thicker overall width in the contracted muscle. Now let's take a look at the muscle contraction process at the molecular level. So the first thing you need to know is I want to talk to you about the relationship of these two right here, actin and myosin. Oh my goodness. If I could tell you anything about myosin, it's that it loves to bind to actin. And so actin, in this case, has a couple binding sites, and they're a little tricky to see. You can almost see them here. They look like little purple circles on the top. Here's some over here that are easier to see. And those are the place where myosin can bind to actin. It can't bind to it at any other position on that particular monomer, okay? So that's where it's got to hit. As you can see here, this is a good one right here on number 3. We can see it's actually touching and binding to one of those little binding sites, right? So that's an active site. What happens there is myosin is going to grab onto actin when it's able to, and then throw it in what we call the power stroke closer to its center M line, right? Climbing up that huge chain of actin. Some other players I need to tell you about. As you'll notice probably right about, here, there seems to be something covering all of those binding sites. And that's true. It's a different kind of protein. It holds a velvet rope over between the actin and the myosin. It prevents myosin from binding directly to actin, and we call it tropomyosin. So tropomyosin, think of it as the tropo. It's like got a ropo in front of the binding site on actin so that myosin can't get too close. So myosin has to sit there and wait until something moves tropomyosin out of the way. All right, well, what's going to move it out of the way? It's going to be this guy right here, troponin. Troponin, shown here to be this teeny tiny little kind of, it looks like a piece of popcorn molecule here. As you can see, it's stabilizing the tropomyosin. It's holding it in place. It's keeping it so all the binding sites are covered so that actin and myosin cannot bind. This is what we find in muscle that is relaxed, right? Non-bound. These sarcomeres are at their greatest, most relaxed length. Okay? All right. Let's get that eraser. There it is. There it is. Okay. So moving forward. So there's one thing, though, the troponin will move out of the way in order to expose binding sites. And that one thing is its favorite snack, calcium. Just loves it. Will bind to it right away, very readily, as you can see here. In the presence of calcium, what happens is troponin changes shape just to grab on when it grabs onto calcium, and that means that something happens to that line. It means that all of a sudden these binding sites, oh, let's do a better job. All right, these little binding sites, there they are, become exposed, and myosin is not going to miss that opportunity. So myosin reaches up and grabs onto as much of that actin as it can in that power stroke. It's like, let's see if I can do it off to the side. It's like grabs onto actin and pulls it, and the next one grabs onto actin and pulls it, and it brings it in towards that M line. Okay, that's the power stroke. During that process, ATP, as you can see here, phosphorylates the myosin, right? And then launches off as soon as myosin is binding to actin, okay? So that's how we get into that conformational shape. In order for myosin to be released, however, or for the muscle to then relax out of the contraction, what happens is all of that calcium needs to be pumped out of the cell, right? So there it goes, and now we're back to this state. That calcium comes in from the sarcolemma. Let's take a look at that process a little bit more closely now. There's the sarcolemma, and it's got this amazing thing just lying underneath it. So surrounding the myofibrils is this sarcoplasmic reticulum. Ooh, let me switch colors. There we go. Is the sarcoplasmic reticulum right here. So sarcoplasm, because it's it's surrounding the sarcomere, it's under the sarcolemma, it's part of muscle. And reticulum, because it's reticulated when you look at it. A reticulation, think of like reticulated python or reticulated giraffe. It's kind of a spotty pattern, but it's not really that organized. It's just kind of general weird looking spots. And if you were to look at the sarcoplasmic reticulum, it kind of has that same form, doesn't it? There's kind of these holes here, these spots, but they're not really that uniform. That's reticulation. So we call it the sarcoplasmic reticulum. That sarcoplasmic reticulum is also clustered together using the T-tubule system, okay, as well as the cisterns. So what do? They're basically like a giant calcium bank. They hold on to calcium when muscle is relaxed. And when muscle needs to contract, they open up their floodgates and let all of the calcium in onto the myofibrils. The sarcomeres then are affected by it because all the troponin wants to grab it. Then it moves the tropomyosin out of the way, and binding happens between myosin and actin, closing up that gap and shortening the muscle in a contraction. Now, how do you get, I guess, uncontracted or just regularly relaxed? You're going to need to pump that calcium out of those myofibrils and into the sarcoplasmic reticulum bank again. So that's where calcium's held, and that's how we control the contraction and relaxation process. It's all about pumping calcium in and out of the system. Here's another little schematic. So here, I kind of want to walk through it backwards. All right, so now we have a contraction. We see here some myosin, and it's bound to some actin, just like we would expect. And why is it? Well, just like we talked about, there is an influx or an inflow of calcium ions coming in from the T-tubule system and the sarcoplasmic reticulum. Now, how did it get started dumping out all that calcium? That's an important question. Why is it starting to move calcium towards the myofibrils instead of pumping them out or away? And the reason's pretty simple. In this case, for this particular muscle, it's because it has been excited by a neuron, and that neuron says one thing to muscle, acetylcholine. That's the neurotransmitter, and that transmitter only says one thing, contract. If you're a muscle and you hear a neuron talk to you, it's going to say only one thing. There's only one word, acetylcholine. And then as soon as you hear it, acetylcholine, oh, contract, release the calcium. That's what it does. So that's how the nervous system excites a muscle, thus releasing the calcium and allowing for the contraction process to take place. So let's review. All right, going backwards. So you have a need to, I don't know, run, jump, pick up your pencil, scratch your nose, whatever it is. You send a nerve impulse down until it reaches this terminal button, right? It's where the axon meets and touches the surface of the muscle cell or the muscle fiber itself. It releases a neurotransmitter called acetylcholine. That acetylcholine is like a word that tells muscle the one thing it can: contract. So the acetylcholine stimulates for the muscle cell to start using the T-tubule system and the sarcoplasmic reticulum to distribute tons and tons of calcium from that reservoir or bank inside the T-tubule sarcoplasmic reticulum directly down into the myofibrils. When the myofibrils are flooded with calcium, the troponin gets super excited and grabs as much of that calcium as it can. After it binds to it, it forgets about its job holding down that velvet rope that's separating actin and myosin, and now all of a sudden some of the rope slips out of the way and myosin is allowed to make cross bridges or link or bind to that actin, and it does so over and over, pulling that actin closer and closer together, shortening the muscle, causing an overall muscle contraction in the muscle organ itself. All right, so let's look again. So the sarcoplasmic reticulum and the T-tubule system. Ooh, sorry about the formatting. Something must have happened. Anyway, so the sarcoplasmic reticulum, as shown right here, that reticulated pattern, that reticulated system that holds all the calcium, right? Remember, it's this calcium, that's Ca2+, right? Also Ca2+, right? Either or, it's the same thing. But anyway, it holds a whole bunch of calcium. It's a reservoir, it's a bank for calcium, because we don't want the muscle to be flooded all the time. If it was flooded all the time, the muscle would be contracted all the time, and that would mean you would essentially be in a state of permanent contraction, never be able to relax, and that's no fun. So, right, I guess we'll go to the next one. Right, the molecular level. So remembering what we do at the molecular level. The ones you need to worry about: myosin and actin are the first and two most important proteins for you to know. Actin and myosin bind together. Myosin wants to bind to actin so much that it grabs it and pulls it closer and closer and closer to its M-line or center bundle point. It allows for the contraction of muscle, thus the shortening of the sarcomere and the shortening of the overall muscle, making it nice and bulky in the middle. That's just like the contraction of the overall organ. It is the overall contraction of the overall organ. Anyway, so there's a couple of other proteins you need to remember too. One being tropomyosin. It's the rope that's held over the binding site of the actin. It stops myosin from grabbing actin at any time it wants, right? And that's held in place by this one, troponin. And troponin is pretty good at keeping that tropomyosin in place. It's really good at making sure myosin is not bound to actin. However, should there be an entry of, say, calcium, troponin loves it, and it binds to it, as seen here and here. And as soon as it has its own calcium, it kind of forgets its job, and it lifts, exposing these binding sites of actin. And who's not going to miss that opportunity? That's going to be myosin right here. So as you can see, myosin's going to bind immediately, begin the contraction, and thus use the power stroke to pull, as you can see, pull the actin directionally closer to its center point, or M-line. Here we are. So this is the relaxed muscle fiber, as you can see here, at its greatest distance and width. There's the least amount of overlap between the actin and myosin. As calcium enters the cell, or well, I should say enters the system of myofibrils, we see there's more and more overlap because all that myosin is grabbing and pulling repeatedly the actin towards it until we reach the final contraction point. So you can see we have maximum overlap. That little sarcomere is at its fattest, right? It's the chubbiest point, and it's kind of characteristic of this happening right here in the contracting bicep of the overall organ, right? The other thing that's important to remember is that it's now shorter. Boop. So if here is where the limits of the relaxed sarcomere should be, right? And there's all this distance now from its original point up here, you can also see that reflected in the larger organ itself. So here's like the terminal reaches of the muscle fibers, and then compare that here with the relaxed muscle. As you can see, it's much broader, all this extra space now, right? So the muscle contracts, making the sarcomere shorter. It also makes it a little bit thicker in the middle. And when there's lots and lots of myofibrils doing that inside of lots and lots of muscle fibers, it means that larger organ physically does the same things. So the same principles apply obviously to single fibers as is the entire muscle itself, as we just looked at. Muscles that are contracted are a little bit fatter and a little bit shorter, and muscles that are relaxed are a little bit further away and they're a little bit longer, right? And of course thinner in the middle. So what contraction actually does is it produces muscle tension. And what muscle tension is it's defined as the force that's exerted on a load or some object to be moved. So contraction, tighter and tighter contractions that is, mean that more and more muscle tension is present in the overall muscle. So that's the basics of the muscle contraction at the smallest level. We looked at the sarcomere, the role of the sarcolemma, sarcoplasmic reticulum, and T-tubule system, and what that means in terms of the differences between a relaxed muscle and a contracted muscle. We looked at some of the important proteins too, things like actin, myosin, troponin, tropomyosin, important ions like calcium, and all the roles that they play. All right, well, if you have any questions, please feel free to email me, and I hope you have a great day.